In our last video, we spent a lot of time talking about terms related to polarity. Polar versus nonpolar, water soluble versus water insoluble, hydrophilic, hydrophobic, and lipophilic. And I also mentioned that really there's a continuum between things that are very polar and very nonpolar. And the highest level skill we want you to have is to be able to rank things out as we did at the bottom of the page. Now, the last thing we want to cover in this review unit is a new idea probably for most of you, and it's a third line on this chart. We have things that are polar, we have things that are nonpolar, but what about things that are part polar and part nonpolar? And I'm not talking about things that are in the middle here. I'm talking about a very different class of molecule. I want to tell you first that these are going to be called amphipathic molecules. We sometimes refer to them as amphiphilic. I treat those two terms as the same thing, but amphipathic is probably going to be the one that I use the most. Let's go to the next page, and we'll return and fill that chart in a little bit more later. When I say part polar and part nonpolar, I don't mean just intermediate polarity. What I mean is we have a large molecule and we can draw a line somewhere in that molecule, and on one side of it we have a very non-polar portion. In this case you can see a bunch of carbon hydrogens in a chain, and in the other part we have something that is very polar. And in this case, as it often is, it's actually charged, which, as we said in the previous video, means the most polar thing we can have. Now, this, as it turns out, is a completely different class of molecule. It's called an amphipathic molecule. It's a whole different beast in terms of how it behaves. And I also want to tell you a little aside about this from our everyday life. The molecule we have shown here is something we're going to cover later in the class, but it's also found in our everyday existence. This is soap. Especially if we take that carboxylate functional group and use a counterion like a sodium ion. That right there is what soap is. Now, polar and nonpolar is something we're interested in because we want to know whether things are water soluble or not. Think about soap. If you were to leave that in a pool of water, a bar of soap in a pool of water overnight, would it dissolve? Is it water soluble? You probably would say, well, it might get all mushy and it might kind of disperse in the water a little bit, but it wouldn't dissolve. It doesn't become clear. But at the same time, it's not water insoluble because it kind of mushes out and becomes part of the water. Actually, it takes on an entirely different phenomenon in water. What these molecules, which we formally call fatty acids but are soap molecules, what they do in water is shown on the right. All of the non-polar tails will congregate together, clustering away from water through the hydrophobic effect. All of the polar heads are going to interact beautifully, as we would expect they would, with waters out here. So we have all sorts of water interacting in a polar fashion through hydrogen bonds with the carboxylates. And this looks like a circle, like a disc, but it's actually a three-dimensional sphere. And this is a special type of interaction, and we call this a micelle. Things that are amphipathic are micelle forming, and that's where the hydrophobics come together, and the hydrophilic portions, the charges, the polar parts are going to interact with the water. So let's go back and fill in the details about that. Part polar, part nonpolar is going to be micelle forming. Now, aside from soap, we're not super interested in micelles in this class, but we are interested in micellar type behavior, and a lot of molecules in the body have micellar type behavior, and I want to just show you one really quick. Turns out that membranes are formed from amphipathic molecules. We are going to cover this in a later chapter, but I just want to introduce this idea to you because it's so important in biology. Amphipathic membrane molecules have a polar head, charged, and then two nonpolar tails. So if we put these molecules in water, the two nonpolar tails come together through the hydrophobic effect, and the polar heads interact with water. This is what we call a membrane bilayer, and we just can't do justice to it on a two-dimensional page. We're going to take a look at this in a lot more detail later, but I do want to bring up one fact here, and that is if we wanted a molecule to cross a membrane from, say, the outside of a cell to the inside of a cell, then it's going to do so based on its polarity. Let's take, for example, a potassium ion. In order for a potassium ion to go through a cell membrane, for instance, to get from the outside of a cell to the inside of a cell, it needs to go through this nonpolar area that is the nonpolar tails coming together. And this is slow. So slow as to be almost non-existent. I want to summarize this little fact by writing this down. It is almost impossible to drag a full charge through a membrane. That brings together a lot of ideas we've talked about: charge, polarity, micelles and amphipathic molecules. I'm really bringing it up here now because it's useful as we go through the next couple of chapters to think about membranes, because they're so important in biochemistry, and to think about how, for instance, drugs and other molecules that we're going to learn about are going to pass through membranes. It's very, very difficult to get full charges through a membrane. Let's leave it at that, and we'll follow up with some homework exercises on this topic.